Hey guys, welcome back to week 2 of my series where I learn ML through an optimization perspective. This week I'm in the Boyd book and I just finished up chapter 2.1 and chapter 2.2 and completed all the exercises. Oh, and a little change of scenery because I'm in Japan. So this really was the first week where I really dove deep and got my hands dirty. So I'm a big fan of linear algebra, having watched Gilbert Strang's OpenCourseWare series a while back. So I'm happy to see a lot of it in the first couple sections. I saw many applications of eigenvalues and eigenvectors, and with positive semi-definite matrices at play. We also saw a bunch of vector spaces and subspaces when talking about affine sets. For instance, I learned that affine sets can be thought of as a subspace plus an offset. So I really like the book so far because they give many different perspectives to think about identical topics, but each serve to better understand that idea. For example, a hyperplane is just a plane in some dimensional space, like a paper sort of extending to infinity in three-dimensional space, or a line in 2D. But it can be thought of just as a point on the hyperplane plus all vectors orthogonal to the vector which defines hyperplane. This has important implications for hyperspaces, which are just the space to the left or to the right of said hyperplane. So I think I'll talk more about this later and show you some math because I think it's pretty cool. Lastly, I did all the exercises from 2.1 and 2.2. There are about 15 in total. I could solve most of them in a reasonable amount of time, but some were very, very difficult and required a series of like clever manipulations, which I don't think I could have thought of. However, I could feel myself understanding the concepts better as I slowly worked through the problems. So firstly, I learned what affine sets are. So a set is affine if a line through any two distinct points in C, where C is a set, also lies in C. So to see what that means, consider the image. So the set C that we're interested in here is a half space defined by y is greater than or equal to 0 in the two-dimensional plane. So we can see that if you pick any 2 points here, denoted by point 2 and point 1, and then draw a line going through them, you'll see that the line eventually reaches on the left side values where the y is less than 0. So the half space is not an affine set. On the other hand, the line itself, so the red line, is an affine set, because if you take any 2 points on the red line and then draw a line between them that goes on forever, well, you just retain the same red line, which of course is contained in the set. I also learned about affine holes, which can be thought of as given any set C, affine holes is the smallest affine set which contains C. So after working through the affine stuff, we went on to convex sets, which are also affine, but the only difference is that we require that if the line segment through any two distinct points in C also lies in C. So the only difference is that the word segment. So you can see here in the picture, we don't have an entire line. We only have a line segment. And so again, you just pick 2 points, anywhere in the set. And if it must be the case that the line segment is also in the set, then it's convex. So in the same picture as before, we can see that the half space is actually convex because you pick any 2 points, and obviously the line segment is going to be in the set as well. So half spaces are convex but not affine. So then similarly to affine holes, we learn about convex holes, which is simply just the smallest convex set containing C. So for example, if C are 5 dots, we want to find a convex set which contains all 5 dots, which is the smallest. And you can see that denoted by the blue lines, this is the smallest we can do. Okay, as stated earlier, I would like to show you the geometry of a hyperplane. Just take an example of a hyperplane in two-dimensional space. So just this plane here. We can see the blue line, which is a hyperplane, that is just simply the points along the plane. So it's defined as such. But if we know the perpendicular vector and we know x0, then we can also form this hyperplane. So in other words, we have the second definition, which defines a hyperplane by the orthogonality of A and a base point in the hyperplane x0. And so in the equation, we can see that the dot product within A and the difference between x and x0 must be 0. And so that what that means geometrically is that A is perpendicular to the difference between x and x0. So we can see in this picture that we have x0 here and x. So take the difference, that's simply just this vector here, and indeed A is perpendicular to that vector. So the hyperplane, therefore, is simply all such vectors that are formed from x minus x0, which is perpendicular to A. Now, a half space is simply the space to the left or to the right of these hyperplanes. So here's a question. Given any vector centered at x0, how do we determine if it's inside the half space? Here's an example of what I mean. So we have a green vector, which is what we want to determine if it lies in the half space. So how do we determine if it's in the half space? Well, the key is using the perpendicular property of A. And so the idea is simple. All we need to do is, in our case, since the half space is to the right of the hyperplane, we measure the angle between the new vector and the A vector, and it's obtuse. So that what that means is that it's not in the half space. That's it. Now you might be wondering, great, but how does all of this sort of relate to machine learning? Well, to answer that question, consider the classic example of binary classification. So what your space might look like is you have the red dots, which is class 1, and the blue dots, class 2. And what you're really trying to do is you're trying to find your best hyperplane such that it separates the space into two half spaces, which contain the most of class 1 and the most of class 2. So there's many extensions to this basic machine learning algorithm, but this is the basic idea. Oh, and by the way, the hyperplane is an affine set, right? Okay, so in the interest of time, I'm going to go quickly through the rest of the topics I learned. So I learned about ellipsoids, which are defined by some center vector here in the center, and a P matrix, where P is symmetric and positive definite. The eigenvectors of P point in the direction of the principal axes, so these directions here. And the square root of eigenvalues are the lengths of those principal axes. I also learned about norm balls and normal cones. On the screen here, you can see an L2 norm ball. Polyhedrons were also included, which I studied extensively in my linear programming class because, linear programming is all about studying these shapes, polyhedrons. We talked about before, but you're given a cost vector pointing in some direction. You want to find the vertex on the polyhedron, which maximizes the objective. Finally, I learned about simplexes, which are basically the simplest possible shape in n dimensions. So you need n plus 1 vertices um, in n dimensions, right? So for n equals 2, we have 3 vertices of a triangle. Finally, I learned about positive semi-definite cones. So this week really was a big one with lots of material. For me, it was difficult not only because of math, obviously, but because I needed to refresh myself a little bit on the linear algebra. But it was also difficult because it was a lot of jumping around topics, as you can tell. But actually, each topic were really related to each other, and I spent a considerable amount of time understanding the connection between each of them. But through writing notes and really trying my best to work through the problems, I really felt like my understanding was improving as I went through that. So next week I'm going to continue to review the material I just learned and then work through the next section. So I'll see you guys next week.